Some of the most recognizable gemstones on Earth are not locked inside vaults. They are scattered across hiking trails, mixed into river gravel, and embedded in rocks most people never think to examine. Entire crystal structures form an environment so common, they are sometimes used as road material. The difference between an ordinary stone and a gemstone is often not rarity. It is recognition. And once that shift happens, landscapes that once appeared ordinary begin to look very different. Starting with a mineral so widespread, it quietly exists in places few would think to search. Let's begin with number 10. Ranked 10th, quartz. Some of the most structurally perfect gemstones on Earth are also among the easiest to overlook. Quartz forms in an extraordinary range of geological environments, appearing in places so ordinary that its presence rarely attracts attention. Crushed stone used in construction often contains quartz fragments. River gravel frequently carries worn crystal pieces shaped by years of natural transport. Even exposed rock faces along hiking trails can reveal small crystal growths where silica-rich fluids once cooled and solidified. The defining feature of quartz is not rarity, but consistency. Its atomic structure arranges silicon and oxygen in a repeating lattice that naturally produces six-sided crystal symmetry. Under ideal growth conditions, this internal order expresses itself externally through recognizable crystal points, transparent or milky formations that appear almost intentional in their geometry. Yet most quartz never reaches the clarity associated with jewelry. Instead, it forms in massive deposits, often mixed with other minerals, creating surfaces that appear unremarkable at first glance. Weathering gradually breaks apart surrounding rock, releasing individual fragments into soil, sand, and sediment. Over time, these fragments travel far from their place of origin, blending into environments where few would suspect a gemstone could exist. Recognition changes everything. A surface once dismissed as ordinary gravel begins to reveal repeating angles, reflective planes, and subtle translucency. Light interacts with fractured surfaces, producing faint internal reflections that distinguish quartz from surrounding material. Entire landscapes can contain significant quantities of crystalline material without drawing attention. This accessibility has made quartz one of the most historically influential minerals, used in tools, timekeeping technology, and optical instruments. Its piezoelectric properties even allow it to convert mechanical pressure into electrical signals, demonstrating how a common mineral can possess highly specialized physical behavior. Quartz often represents the moment when perception shifts. The realization that gemstones are not always hidden in remote or inaccessible environments challenges the assumption that rarity defines importance. Sometimes what appears common simply has not been examined closely enough. And once that possibility becomes visible, the search begins to change. Because the next stone on this list was once considered so valuable, its color became associated with power itself. Moving to number 9, ranked 9th, amethyst. For much of recorded history, purple gemstones occupied a position few materials could rival. Color alone defined status. The deep violet associated with amethyst was once restricted to royalty, clergy, and ruling elites. Its rarity in early trade networks elevated its symbolic value, placing it alongside gemstones that required extraordinary effort to obtain. Yet the geological story behind amethyst reveals a very different reality. Amethyst is a variety of quartz, colored by trace amounts of iron exposed to natural irradiation over long periods of time. Under the right conditions, silica-rich fluids enter cavities within volcanic rock. As temperatures gradually decrease, crystals begin forming inward from the walls of these voids, layer by layer, producing clusters of pointed terminations. These cavities, known as geodes, can remain hidden within otherwise ordinary basalt formations for millions of years. When erosion eventually exposes them, fragments may separate from their original host rock and travel downstream, sometimes appearing in areas far removed from the volcanic environments where they first formed. Externally, an unbroken geode often appears indistinguishable from surrounding stones, rounded, weathered, and muted in color. The transformation occurs only when the interior becomes visible. Inside, tightly packed crystal points reflect light across natural facets, producing shades ranging from pale lavender to saturated violet. Variations in temperature, Iron concentration and radiation exposure influence the intensity of color, making each formation subtly different. Large deposits discovered in Brazil and Uruguay dramatically expanded global availability, shifting amethyst from a gemstone reserved for elites to one accessible to collectors at nearly every level. This shift did not diminish its structural or optical interest. Instead, it revealed how perceived rarity can change as geological understanding improves and new sources are discovered. Amethyst illustrates an important principle. Value perception often evolves faster than the minerals themselves. A gemstone once considered exceptionally rare may become widely available once formation environments are better understood, and once color begins to stand out against otherwise neutral surroundings, the eye becomes more sensitive to pattern. Because the next gemstone on this list does not rely on color alone to attract attention. Its natural geometry creates forms so precise, they appear almost deliberately shaped. Moving to number 8, ranked 8th, garnet. Not all gemstones reveal themselves through brilliance or transparency. Some become recognizable through structure alone. Garnet often appears as small, dark crystals embedded within metamorphic rock, easily overlooked by those expecting gemstones to display obvious clarity or sparkle. In natural environments, garnet typically forms under conditions of intense heat and pressure, where existing minerals gradually recrystallize into new arrangements, more stable within changing geological forces. The result is a crystal structure defined not by irregular fracture, but by repeating geometric order. Garnet commonly develops in dodecahedral or trapezohedral forms, multi-phase shapes composed of symmetrical planes that intersect at consistent angles. These forms can appear surprisingly precise, particularly when erosion removes surrounding material and exposes individual crystal faces. Rather than appearing polished, garnet often presents as a deep red to reddish-brown mineral with a subdued surface luster. Iron-rich varieties create darker tones that may initially resemble ordinary rock fragments. However, once attention shifts to shape rather than color, patterns begin to emerge. Edges align, faces repeat, angles remain consistent across multiple specimens. These visual cues distinguish garnet from randomly fractured material, revealing the internal order produced by its silicate crystal lattice. Due to its relative hardness, garnet resists weathering more effectively than many surrounding minerals. Over time, softer materials gradually erode away, leaving garnet crystals behind in soils, stream beds, and sediment deposits. In certain locations, small garnet grains accumulate in sand-like concentrations, sometimes visible as subtle reddish specks when observed under adequate lighting. Historically, garnet has been used not only as a gemstone, but also as an abrasive material due to its durability. Its resilience allows crystals to survive long geological transport distances without losing their characteristic shape. Recognition of garnet often marks a transition in how natural materials are observed. Instead of searching only for color or transparency, the eye begins to identify repeating structure, evidence of the organized atomic frameworks that define crystalline minerals. Geometry becomes the signal, and once structure becomes visible, surface patterns begin to attract even greater attention. Because the next gemstone on this list does not depend on crystal faces to create visual interest. Its internal layers form patterns that resemble deliberate design rather than geological coincidence. Moving to number 7, ranked 7th, agate. Few natural materials demonstrate repetition with as much visual precision as agate. At first glance, rough agate often appears indistinguishable from ordinary rounded stones shaped by water and time. Its outer surface is typically matte, weathered, and muted in color, offering little indication of the intricate structures concealed within. The transformation occurs only when the internal structure becomes visible. Agate forms through a gradual process in which silica-rich fluids enter cavities within volcanic rock. Over extended periods, microscopic layers of quartz deposit sequentially along the interior walls of these voids. Each layer reflects subtle changes in temperature, pressure, and mineral content, creating bands that vary slightly in color and opacity. The result is a sequence of concentric patterns that may appear almost deliberate in their organization. Parallel lines curve inward, intersect, and repeat with remarkable consistency. Some formations display high contrast between light and dark bands, while others present soft transitions between translucent layers. Even under magnification, the layered arrangement reveals a continuity that suggests controlled formation, despite being entirely natural. Because agate often forms in nodules, weathering gradually separates these rounded structures from surrounding host rock. Water movement smooths their surfaces, allowing them to travel through riverbeds or accumulate in sedimentary environments where they may remain unnoticed among more common stones. The appeal of agate lies not in singular color, but in variation. No two banding structures are identical. Each specimen preserves a record of changing geological conditions during its formation, effectively capturing a timeline within mineral layers measured in fractions of millimeters. Cut or polished surfaces reveal these internal patterns with greater clarity, often transforming an otherwise modest exterior into a detailed composition of repeating geometry and natural contrast. Recognition of agate often changes how patterned materials are perceived in natural environments. Instead of searching for transparency or crystal faces, attention shifts toward texture and structure embedded beneath the surface. Visual complexity becomes the signal, and once layered formation becomes recognizable, even stones lacking strong banding begin to reveal subtle variations in color shaped by mineral impurities. Because the next gemstone on this list rarely displays dramatic patterning, its appeal comes from dense color saturation formed through the presence of iron-rich inclusions distributed throughout the stone itself. Moving to number 6, ranked 6th, Jasper. Not every gemstone announces itself through transparency or reflective brilliance. Some reveal their presence through density of color alone. Jasper often appears as smooth, opaque fragments shaped by long periods of natural erosion. Its surface rarely produces the visual signals commonly associated with gemstones. Instead of crystal faces or internal light return, jasper presents as a compact material defined by uniform structure and rich saturation of earthy tones. Iron inclusions dispersed throughout the silica matrix create colors ranging from deep red and burnt orange to mustard yellow, olive green, and muted brown. These colors form without visible layering, producing a visual impression that feels solid rather than translucent. Because jasper commonly develops within sedimentary environments, it frequently occurs in areas influenced by historical water movement. Over extended periods of transport, rough edges gradually soften, creating rounded surfaces that blend easily among ordinary stones. This visual subtlety contributes to why jasper often goes unrecognized. Without strong banding patterns or crystalline transparency, it may appear indistinguishable from other compact rocks. Yet its internal composition reveals a microcrystalline quartz structure similar to Chalcedony and agate, demonstrating how variation in impurities can significantly alter appearance without changing fundamental mineral classification. Historically, jasper has been used for tools, seals, and decorative objects due to its durability and consistent fracture behavior. Its hardness allows it to retain polish effectively, enhancing color depth and surface smoothness when cut. However, in natural environments, jasper typically appears understated. Recognition depends less on visual contrast and more on sensitivity to subtle uniform coloration that differs from surrounding material. The absence of obvious pattern becomes part of the identification process. This introduces an important shift in observation. Gemstones are not always defined by brilliance or dramatic internal effects. Sometimes their defining characteristic is stability, color distributed evenly across a material formed under consistent geological conditions. Understanding jasper often leads to a broader realization. Several stones encountered so far share a related internal structure, despite appearing visually different. Because the next entry on this list reveals how multiple gemstones can originate from the same mineral family, distinguished primarily by differences in texture, translucency, and trace elements. Moving to number 5, ranked 5th, Chalcedony. At this stage, a pattern begins to emerge, not in color or external appearance, but in internal structure. Several gemstones already encountered share a common origin despite presenting very different visual characteristics. Quartz, agate, and jasper may appear unrelated at first glance, yet each belongs to a broader mineral grouping defined by silicon dioxide arranged in microscopic crystalline formations. Chalcedony represents this connection. Unlike quartz crystals that grow large enough to display distinct geometric faces, Chalcedony forms from aggregates of crystals too small to be individually visible without magnification. These interlocking microscopic structures create a compact material that can appear translucent, opaque, patterned, or uniform depending on the presence of trace elements and environmental conditions during formation. This explains why agate develops banding patterns while jasper displays consistent coloration. Both originate from silica-rich fluids that gradually solidify within cavities, fractures, or sedimentary spaces. Variations in temperature, mineral content, and growth rate influence how these microscopic crystals arrange themselves, producing a wide range of visual outcomes despite sharing nearly identical chemical composition. Chalcedony often appears in environments influenced by volcanic or hydrothermal activity, where silica becomes dissolved in heated water before slowly precipitating as conditions stabilize. Over time, repeated cycles of mineral deposition create dense formations capable of surviving erosion and transport across considerable distances. Its presence frequently goes unnoticed because Chalcedony rarely exhibits the large, reflective crystal faces associated with traditional gemstone imagery. Instead, it reveals itself through texture, waxy luster, subtle translucency, or muted color transitions that become more apparent under consistent lighting. Recognition of chalcedony often reshapes understanding of what defines variety within mineral species. Differences that appear significant visually may result from relatively minor variations in trace chemistry or growth environment. This realization creates a conceptual turning point. The diversity observed among gemstones does not always reflect completely different materials, but rather different expressions of similar structural foundations. Once internal structure becomes the reference point, new visual phenomena begin to stand out more clearly, because the next gemstone on this list introduces an optical effect that changes depending on how light interacts with fibrous internal architecture. Moving to number 4, ranked 4th. Tiger's eye. Movement is rarely associated with stone. Most minerals appear static, their visual character unchanged regardless of viewing angle. Tiger's eye challenges that expectation through an optical phenomenon that creates the illusion of motion across its surface. A narrow band of reflected light appears to glide as the stone shifts position, resembling the focused gaze of an eye observing from within the material itself. This effect, known as chatoyancy, develops through a highly specific internal structure. Parallel fibrous inclusions form within the quartz matrix, aligned in a consistent direction during mineral growth. As light enters the polished surface, these microscopic fibers reflect illumination in a concentrated band, producing a luminous streak that moves relative to the viewer's perspective. Unlike reflective sparkle created by faceted gemstones, chatoyancy produces a continuous, fluid line of light rather than scattered flashes. In natural environments, rough tiger's eye rarely displays this effect clearly. Its surface may appear dull or layered, often showing muted golden-brown coloration, without revealing the optical behavior hidden within. Only when the material is cut parallel to the orientation of its internal fibers does the characteristic reflective band become visible. Deposits of tiger's eye frequently occur in regions shaped by significant geological transformation, where silica gradually replaces earlier fibrous minerals through a process of pseudomorphism. The resulting structure preserves the directional alignment of the original fibers, allowing the optical phenomenon to persist even after the material composition changes. This combination of structural order and mineral replacement creates a gemstone defined not only by color, but by interaction with light itself. Observation of tiger's eye introduces a new dimension to gemstone identification. Visual interest no longer depends solely on color, variation, or external crystal geometry, but on internal organization that influences how light behaves across the surface. Once attention becomes attuned to optical effects, even subtle structural alignment can become recognizable under changing illumination. The eye begins to anticipate motion within materials previously considered static, because the next gemstone on this list demonstrates precision of a different kind, not through moving light, but through crystal forms so geometrically exact that they appear almost artificially constructed. Moving to number 3, ranked third, fluorite. Perfect cubes are rarely associated with natural formation. Sharp edges, flat faces, and proportional symmetry are typically linked to human design, where precision tools control angles and dimensions. Fluorite challenges this expectation by forming crystals whose geometry appears almost deliberately engineered. Under suitable geological conditions, fluorite develops in cubic structures defined by repeating atomic arrangements that extend uniformly in 3 dimensions. The mineral's internal lattice naturally encourages growth along axes that intersect at consistent right angles, producing crystal forms that display remarkable structural regularity. When multiple crystals grow in proximity, clusters of interlocking cubes may form, each maintaining consistent angular relationships despite variations in size. Transparent or translucent faces reflect light in a way that emphasizes edges, making geometric boundaries more visually distinct than in many other minerals. Color variation in fluorite results from trace elements and structural imperfections within the crystal lattice. Purple, green, yellow, and colorless varieties may appear within the same geological region, sometimes even within a single specimen where growth conditions shifted over time. In natural settings, fluorite is often associated with hydrothermal environments where mineral-rich fluids circulate through fractures in surrounding rock. As temperature and pressure conditions gradually stabilize, dissolved compounds crystallize along cavity walls, allowing geometric forms to develop without significant external interference. Because fluorite has a relatively low hardness compared to quartz, well-formed crystals may display minor surface wear if transported over long distances. However, specimens protected within cavities can preserve sharp edges with exceptional clarity. The visual effect is distinctive. Straight lines intersect cleanly. Faces meet at angles rarely observed in irregular mineral fracture. Even without polishing, the crystal form itself communicates internal order. Observation of fluorite often reinforces an understanding that nature frequently produces structures governed by mathematical constraints rather than random arrangement. Symmetry becomes evidence of stability. The appearance of precision does not necessarily imply artificial influence, but rather reflects predictable outcomes of atomic organization under favorable environmental conditions. This recognition expands the criteria by which gemstones are identified. Geometry can become as significant as color or optical behavior, and once expectations of crystalline form are established, the definition of what qualifies as a gemstone may be challenged further, because the next material on this list does not form crystals at all. Moving to number 2, ranked second, obsidian. Not all gemstones are crystalline. Obsidian forms in conditions where crystal growth is interrupted entirely. When molten rock cools so rapidly that atoms cannot arrange themselves into repeating structures, the result is a natural glass rather than a mineral composed of ordered crystal lattices. This process most commonly occurs in volcanic environments where silica-rich lava is exposed to sudden temperature change. Without sufficient time for internal organization, the material solidifies in an amorphous state, lacking the geometric symmetry typically associated with crystalline gemstones. The visual character of obsidian reflects this rapid formation. Surfaces often appear smooth and continuous, with a vitreous luster resembling manufactured glass. Fracture patterns follow curved paths known as conchoidal fractures, producing sharp edges that historically allowed obsidian to be used in cutting tools long before the development of metal technology. Despite lacking crystal faces, obsidian has long been considered a gemstone due to its durability, workability, and distinctive appearance. Variations in composition create subtle differences in visual texture. Small mineral inclusions may produce patterns such as snowflake obsidian, where pale crystalline formations appear suspended within darker glass. Other specimens display faint banding or reflective sheen, depending on how microscopic structures interact with light. Because obsidian forms primarily in regions influenced by past volcanic activity, fragments are sometimes found in areas shaped by ancient lava flows. Weathering gradually separates pieces from larger formations, allowing smaller fragments to accumulate in soils or sediment. Its glass-like appearance often makes identification relatively straightforward once the characteristic surface luster becomes recognizable. Obsidian demonstrates that gemstone classification is not limited solely to crystalline structure. Instead, it reflects a combination of physical properties, historical use, and visual distinctiveness. This challenges a common assumption that gemstones must display geometric order at the microscopic level. Structure can vary dramatically while still producing materials valued for their natural origin and aesthetic qualities. Once the expectation of crystal symmetry is removed, the definition of what qualifies as a gemstone expands considerably, because the final entry on this list returns to crystal structure once again, but in a form so widespread that it appears in some of the most familiar geological materials on Earth. Moving to number 1. In first place, calcite. Some of the most structurally important minerals on Earth are rarely recognized as gemstones at all. Calcite forms a primary component of limestone and marble, materials widely used in architecture, sculpture, and construction for thousands of years. Entire mountain ranges consist largely of calcite, shaped through biological, chemical, and geological processes that continuously cycle calcium carbonate through natural environments. Despite this abundance, calcite is capable of developing well-defined crystal forms that clearly demonstrate the ordered internal structure characteristic of crystalline minerals. Under suitable conditions, calcite produces rhombohedral crystals distinguished by repeating angled faces that intersect in consistent geometric relationships. These crystal forms often appear within cavities in sedimentary rock, where mineral-rich solutions gradually deposit layers over extended periods of time. Colorless varieties may display a level of transparency that reveals an optical effect known as double refraction. Light passing through transparent calcite separates into two rays, causing objects viewed through the crystal to appear duplicated. This phenomenon results directly from the internal arrangement of atoms, which influences how light travels through the material. The presence of calcite in familiar materials, such as limestone cliffs, cave formations, and marble surfaces demonstrates how gemstones can exist within environments rarely associated with mineral collecting. Stalactites and stalagmites found in cave systems develop through slow deposition of calcite as mineral-rich water evaporates drop by drop. Over long timescales, repeated accumulation creates formations that preserve visible evidence of gradual crystal growth. Calcite illustrates a fundamental principle underlying the concept of gemstone rarity. Availability does not necessarily diminish geological significance. Instead, significance often depends on how internal structure expresses itself in observable form. When crystal faces become visible, even common minerals can reveal characteristics typically associated with more traditionally recognized gemstones. Recognition alters perception. Materials once considered purely structural begin to display features shaped by precise atomic organization. The distinction between ordinary stone and gemstone becomes less defined by scarcity and more influenced by awareness. Once crystal structure becomes identifiable in familiar environments, the landscape itself begins to appear more complex. What once appeared uniform begins to reveal variation. What once appeared common begins to display structure, and the idea that gemstones must always be rare begins to change. Rarity is often misunderstood. Some gemstones are rare because formation conditions are extremely specific. Others appear common simply because the environments that produce them occur more frequently across the Earth's surface. But accessibility does not make these minerals less remarkable. Each crystal structure represents a stable arrangement of atoms formed under precise combinations of temperature, pressure, and chemical availability. Conditions that must remain consistent long enough for internal order to develop. Once these patterns become recognizable, environments that once appeared visually uniform begin to reveal variation in structure, texture, and composition. The search for gemstones often begins with rarity, but understanding often begins with what is easiest to find. In the next episode, attention shifts from accessibility to misconception. Some of the most overlooked gemstones were ignored for decades, not because they lacked rarity, but because their true identity was not fully understood. And once recognition changed, so did demand.